And I guess we have a former University of Michigan student. She's now at the University of Florida, Emily Quapis, who's going to give a talk about the development of methodologies for nuclear explosion monitoring.
So is that all good? You can hear me and see my screen?
Loud and clear, whenever you're ready.
Okay, yeah, so I'm Emily. I'm a first-year PhD student in nuclear engineering at the University of Florida, and I work on developing methodologies for nuclear explosion monitoring with Dr. Hartig. There are multiple techniques that are currently used to monitor nuclear explosions. I believe most of you listening today are familiar with the existence of seismic monitoring and radio xenon detection. I fall into this third category of optical sensing. By using ultra-fast laser ablation, we are able to produce laser-produced plasma plumes, or LPPs, that are representative of high explosives and nuclear fireballs. Hence, we have a laboratory scale method to characterize nuclear fireballs and thereby detect and respond to nuclear explosion events. I'm interested in remote sensing using laser spectroscopy, where I am working on developing the next generation of detectors for standoff, isotopically resolved, and phase identifiable detection of actinides. This would enable rapid mapping and compositional analysis of contamination plumes in post-detonation nuclear environments. Before moving on to the rest of the presentation, I would like to bring to your attention these figures on the right. In atomic and molecular spectroscopy, there are typically hundreds to over 1,000 peaks that are identified for an element over the visible wavelengths. When performing an analysis on an element, typically a select number of these peaks are chosen, such as this isotopic analysis of plutonium dioxide, where 2 peaks have been chosen. Objectives of my research include developing optical signatures for actinides, where I'm focused on actinide plasma chemistry and speciation in the plasma plume. This will move into developing models of the spatial and temporal evolution of the highly transient laser-produced plasma plumes, where I will be working with plutonium and cerium, where cerium would be used as a surrogate for plutonium before plutonium itself is used. And I'm collaborating with Savannah River National Laboratory on this research. I do want to note that this work is very current and ongoing with uranium. To my knowledge, I'm one of the first who will be getting into this work with plutonium. As for the technical approach for this presentation, I'm going to be approaching this from a theoretical standpoint. I haven't been able to do any experimental work for months due to COVID. It was planned to start laser-induced breakdown spectroscopy of cerium in May, and that's been delayed until who knows when. So I'm going to take a theoretical approach in this presentation and compare the chemical and physical properties of uranium to cerium and plutonium to give an insight into what we expect to see in the Lib spectra of cerium and plutonium, since that's not currently available to compare with uranium spectra. The physiochemical properties of an element are dependent on its electronic structure, and so are the optical signatures that we're detecting with our instruments. Hence, similarities in physiochemical properties between these elements should yield similarities between optical signatures. I'm going to go through a brief background on the physical chemistry of actinides, and the main factors in understanding the physical chemistry of actinides is the proximity of the 5f electrons to the localization-delocalization transition, as well as the small energy difference between the 5f and 6d orbitals. This small difference in these valence orbitals results in competing configurations in molecular bonding, which leads to more complex chemistry, such as a higher number of oxidation states, and greater sensitivity to external influences such as pressure. And this diagram here is really the key to understanding that. So what's special about plutonium is that plutonium lies on this transition between localization and delocalization, or superconductivity in this figure. When you're in the localization region, bonding isn't favored, while when you move into the delocalization or superconductivity region, bonding is favored. Since plutonium is on this transition, it can go either way. When you dope plutonium with gallium, such as for weapons grade plutonium, you're pushing plutonium to the right in this figure into the localization region, and that causes the alloy to become less reactive and more corrosion resistant. Since cerium falls between uranium and plutonium along this diagonal, I would expect the physical chemical properties of cerium to be somewhere in between uranium and plutonium. So to approach this from a mathematical standpoint, I've decided to look into the oxidation mechanisms and kinetics of these three elements. Oxidation provides insight into the electronic, thermodynamic, chemical, mechanical properties of an element. And we know that the oxidation properties are the same for lanthanide and actinide oxides of the same oxidation states. And we do see this with plutonium and cerium, where they follow the same oxidation reactions to form a stoichiometric dioxide, while uranium forms a hyperstoichiometric oxide. In literature, there's many empirical growth models that have been developed, but the general consensus is that inverse logarithmic growth models can be used to describe oxidation at low temperatures, such as room temperature, while parabolic models are used at higher temperatures and paralinear models are used at higher temperatures yet. Diffusion coefficients, such as the diffusion of the ionic oxygen through the oxide film, does play a role in certain growth models for oxidation. So I've gone ahead and taken diffusion coefficients from literature to use to produce my models and determine the oxide film thickness as a function of time, which I will show you on the next couple pages. And I do want to note that this disagreement between different cerium oxide data, that's very common to find in literature. There's a lot of disagreement, and I'll go into reasons for that later when I'm going through my results. But what I want to note on this slide right now is that diffusion coefficients are also a function of stoichiometry. So this had to be considered with hyperstoichiometric uranium oxide, because it wasn't a stoichiometric oxide. So my first case study I want to go into is with thin films, where I have my math here if you want to look through this later. But for the sake of time with this presentation, I'm just going to go through this summary slide right here. And with thin films, the Nernst-Einstein relationship is no longer valid, and hence an atomistic model must be used to describe the oxidation, which is driven by the electric field generated by the migration of electrons across the metal oxide interface. And the general conclusion here is that the oxide film is going to approach a limiting thickness as long as the ambient temperature is less than some critical temperature, which is related to the activation energy of the oxidation reaction. And for the three elements I've chosen to show here, they all satisfy this condition. And as expected from physical chemistry, you see that cerium falls between uranium and plutonium along this plot at 25 degrees Celsius in dry air. So to move on to higher temperatures where the parabolic growth model can then be taken at 200 degrees Celsius, you see the same trend between plutonium and uranium and cerium, where cerium once again falls between uranium and plutonium. You see the general trends where unalloyed plutonium is more reactive than plutonium alloyed with gallium. And you see this difference in the oxide thicknesses between the different hyperstoichiometries of uranium oxide, as you expect to see. I do want to note that oxidation data tends to vary largely between measurements and literature. I'm using diffusion coefficients from literature. That's what I have to work with since I can't run experiments myself. And gas composition plays a large role in these disagreements between different published papers. If there's water vapor present in the atmosphere, that leads to enhanced oxidation kinetics and will increase the thickness of the oxide film. So, I mean, the diffusion coefficients I use for plutonium here may not be in dry air, quote unquote dry air, where there was actually water vapor present. So this could easily be half of the thickness that I got, depending on the diffusion coefficients I used. And that's just what I had to work with. But I do want to point out that cerium, you can increase its thickness here by doping cerium with gallium. And that enhances the oxidation kinetics of cerium, which you didn't see with plutonium. But going back to this diagram here, that's exactly what you would expect to see. You dope cerium with gallium, you're shifting it closer to this transition between localization and delocalization, which is going to make it more reactive. And while when you dope plutonium with gallium, since it was already on this transition, you were moving it off into the localization region where it would be less reactive. So like just to wrap up this section here is with relation to Lib spectra, I expect cerium spectra to be more reactive than that of uranium and plutonium to be more reactive than that of cerium. So starting to wrap up this presentation, as soon as I can get to Savannah River National Laboratory, I'll be performing laser-induced breakdown spectroscopy on plutonium and cerium metals, where I'll be focused on, once again, actinide plasma chemistry, looking at the oxidation effects in the plasma plume, and its effect on the emission spectra and the evolution of the plume itself. By investigating plutonium nuclear fireballs with laser-produced plasmas, I expect to gain an informed understanding of the fundamental physiochemical properties of plutonium plumes, and especially if the focus on the molecular species in the plutonium nuclear fireball, as well as the oxidation and atmospheric effects on the emission spectra and plume evolution. Going into the MTV impact, not too much has changed since the presentation I gave in March, so I'm just going to highlight the new additions. My research group has added collaborations with Sandia National Laboratory and AFTAC, the Air Force Technical Applications Center in Florida. And 2 of us have been awarded graduate fellowships with the Department of Defense. In conclusion, this work supports the NNSA mission areas of nuclear nonproliferation and counterterrorism by advancing technologies towards monitoring and responding to nuclear explosion events. Myself and other graduate students in my research group are working on developing these detection techniques. We're participating in internships and research at national laboratories, as well as Department of Defense laboratories. And it's expected that when we graduate, we will obtain full-time employment at a national laboratory or with the government. And for the two of us who were awarded the Department of Defense fellowships, we already have full-time jobs lined up with the Department of Defense. So I would like to thank our sponsors today and the University of Michigan for organizing this event. And I'm happy to take any questions. And here are my references because they were not going to fit on these slides. So thank you.
Thank you very much, Emily. So does anyone have any questions? Either type in chat or just speak up. All right, well, I'm not seeing any questions for Emily, unfortunately. So unfortunately, I can't come up with any too. So I guess if there are none other, I'll just wait a few seconds. We'll then move on to our last speaker. All right, let's all give Emily a virtual round of applause, and we'll queue up for our final speaker.